So, in this video, we will be dissecting lesson 10.3 of Honors Chemistry. If it wasn't so late at night, I would actually be getting through 10.4 and 10.5. Alas, I don't have the time. Potential energy diagrams are diagrams used to show the changes in potential energy that occur during a chemical reaction. You have potential energy of reactants, products, activated complex, heat of reaction, endothermic versus exothermic, effect of a catalyst, forward versus reverse, and activation energy. This is exothermic reaction. Heat is produced and energy is lost. You have a negative delta H. In an endothermic, you have a positive delta H. PE product is greater than PE reactants, and the heat is listed as a reactant in the chemical equation. A reverse reactant is when you go this way, so right to left. Products to back to reactants. In a Maxwell-Boltzmann distribution, you can see the blue area is the amount of particles that have enough energy to react. And you can see that through kinetic energy. And how increasing the T, increasing the energy, will flatten out the curve so more particles will be able to react. The effect of a catalyst is that it speeds up the reaction without being changed in the chemical reaction. No effect on the heat of reaction changes the mechanism of the reaction, and it lowers the activation energy. Also, a greater amount of molecules exceed the required activation energy. So as you can see in this diagram, more can react with a catalyst. And that's just some of the diagrams. So I can actually get to 10.4 honors chemistry in this video as well, which is nice. Don't think I'm going to be getting to 10.5. 10.4 is enthalpy stoichiometry. So enthalpy is a measure of the potential energy stored in chemical bonds of the reactants and products. PE is related to the physical phase. So this again is just like showing the reaction and how you lose 571.6 kilojoules. So the delta heat of reaction is the heat of the products minus the heat of reaction. So in this case, the delta H is negative 393.5 kilojoules. And in this case, with the positive, it's 52.4. Reference table I will show you the heat of reaction for various chemical reactions. Now, the heat of formation is the amount of energy involved in the synthesis of a compound. And the standard heat of formation is when the temperature is 25 degrees Celsius, 298 Kelvin, 77 degrees Fahrenheit, and the pressure is 1 atm, 1.013 kilopascals, 760 millimeters of mercury. So how much heat is released when 40 grams of H2 reacts with excess O2? Do I have this? I need to look if I even have this. This is actually pretty confusing. I'm pretty scared for this chemistry honors test, like mainly as a result of this. But it's fine. You just got to outline, make chem videos, post them onto YouTube. It should be fine. So yeah, you have to do stoichiometry. So 40 grams of H2, over 1 mole of H2, and then you have the negative 43.6 over the 2 moles. And with the 2 grams of that, you do get to that negative 483.6 kilojoules when you do the enthalpy. Generally, if you have a small delta H, it's very unstable. A large negative delta H is extremely stable, and a positive delta H is relatively unstable and can easily decompose. So in this case, this is stable, but these two are unstable with the CO2, NO, and NO2. Hess's law states that the delta H of the overall reaction is the sum of the enthalpy changes for the initial steps, which is based on the first law of thermodynamics. Now, of course, understanding what any of this meant would make life a lot easier. So this is another difficult case where you have to see, like, how much of it is on each side and what side are they on, and you have to like negate anything, and it is really confusing to understand a lot of stuff. So I should study more.